Look up. Just look up on a clear day when an airplane goes over. You see that white line behind it. Pretty, isn't it? Like somebody took a piece of chalk and drew a straight line across a blue blackboard. Most people glance at it, think airplane, and go back to whatever they were doing. But I want you to stay with me on that white line for a while, because that little streak of white is doing something to the sky that you would never guess from looking at it. Let me start with the obvious question. What is that white line? It is a cloud. That's all it is. The airplane made a cloud. Now you might say, well, that's not very interesting. Clouds form all the time. And you'd be right, clouds form all the time. But this cloud did not form because the atmosphere decided it was time to make a cloud. This cloud formed because a machine, flying 6 or 7 miles above your head, at a speed of 500 miles per hour, dumped a particular kind of hot, wet exhaust into air that was unbelievably cold. And something happened in that mixing that is, when you think about it carefully, a beautiful piece of physics. Here is what happens. A jet engine burns kerosene. Kerosene is a hydrocarbon. When you burn a hydrocarbon, you get two main products, carbon dioxide and water. The water comes out as vapor, mixed in with all that hot exhaust gas, at a temperature of maybe 500 or 600 degrees Celsius. Now, outside the airplane, at cruising altitude, the air is cold, very cold. 40 below zero, 50 below zero, sometimes 60 below 0 Celsius. So you have this hot, wet breath from the engine slamming into air that is desperately cold. Think of it like breathing on a winter morning. You walk outside, it is freezing, and you breathe out, and you see your breath. That little puff of fog. Same idea, your breath is warm and moist. The air is cold. The moisture in your breath condenses into tiny droplets, and for a moment you can see it. Then it vanishes, because the air around you, although cold, is not cold enough or wet enough to keep those droplets alive. But notice something about that winter breath. It does not happen in summer. In August, you breathe out, and you see nothing, because the warm air can hold all the moisture your lungs produce without reaching saturation. In January, the cold air cannot hold it, and you get a little puff of cloud. There is a threshold, a dividing line. On one side, your breath is invisible. On the other, it becomes a cloud. The same kind of threshold exists for jet contrails, and it was worked out with lovely precision. A physicist named Erich Schmidt got the basic thermodynamics right in 1940. A meteorologist named Herbert Appelman refined it in 1953. What they showed is that you can draw a line on a chart of temperature versus humidity. Below that line, contrail. Above it, no contrail. The position of the line depends on pressure, humidity, and a quantity related to how much water vapor the engine releases per unit of heat. For a typical modern jet burning kerosene, the threshold is around minus 40 degrees Celsius, but it shifts with conditions. In humid air, contrails appear at slightly warmer temperatures. In bone-dry air, you need it even colder. Up at 35,000 feet, though, the situation is different from your winter breath in another important way. The air is not just cold. It is astonishingly cold. And the exhaust from a jet engine is not just moist. It also contains billions and billions of tiny particles. Soot. Little specks of carbon and sulfur compounds blown out of the engine along with the water vapor and the carbon dioxide. Those particles matter enormously, because water vapor does not like to condense on nothing. It needs a surface. It needs something to grab onto. Physicists call these condensation nuclei, and the jet engine provides them by the trillions. So the water vapor rushes out, hits that frigid air, and immediately starts condensing onto those soot particles. But it does not just condense into liquid droplets. At those temperatures, 40 below and colder, the droplets freeze almost instantly into tiny ice crystals. And there is your white line. It is a trail of ice crystals hanging in the sky behind the airplane. A condensation trail, a contrail. Now most people stop there. Oh, it's ice crystals, fine. But that is where it actually starts getting interesting. Watch that contrail for a while. Sometimes it disappears in seconds. The airplane passes, the white line forms, and it is gone, like riding on water. Other times, though, the contrail stays. It lingers. It hangs there for minutes, then tens of minutes, then hours. And as it hangs there, something happens to it. It starts to spread. The line gets wider, fatter. The edges get fuzzy. What was a sharp white stroke across the sky becomes a broad, hazy smear. And if you come back an hour or two later, you might not even recognize it as a contrail anymore. It looks like a thin, wispy, natural cloud. Why does one contrail vanish in seconds while another one lasts for hours and spreads across half the sky? This is the key question, and the answer tells you everything about what is going on up there. It depends on the air the contrail is born into. If the air at cruising altitude is dry, meaning the humidity is low relative to ice, then those little ice crystals have a problem. They are surrounded by air that wants its water back. The air is undersaturated, it is thirsty, and the ice crystals do what ice does in dry air. They sublimate. They go directly from solid ice back to invisible water vapor without ever passing through the liquid stage. The contrail evaporates. Gone. The sky heals itself. This, by the way, is the same process that makes a snowman shrink on a cold, dry winter day, even when the temperature never rises above freezing. The ice does not melt, it sublimates. Molecules escape directly from the solid surface into the air. If you have ever hung laundry on a clothesline in winter and found that the frozen clothes dried anyway, you have seen sublimation at work. At cruising altitude, the process is fast because the air is so cold and so thin. A contrail in dry air can vanish in 30 seconds. Blink and you miss it. But if the air up there is already humid, already close to being saturated or even supersaturated with respect to ice, then the contrail has stumbled into paradise. Those ice crystals are not surrounded by thirsty air. They are surrounded by air that has more water vapor than it knows what to do with. And that excess water vapor starts depositing onto the ice crystals, making them grow. The crystals get bigger. The contrail gets thicker. And because it is made of ice particles that are now substantial enough to scatter light and interact with radiation, it starts behaving like a cloud. Because it is a cloud. It is an artificial cirrus cloud born from a jet engine, fed by the atmosphere, and now doing everything a natural cirrus cloud does. And what does a cirrus cloud do? This is where we need to slow down and think carefully, because this part is crucial and it is subtle. A cirrus cloud, way up high, made of ice crystals, interacts with two different kinds of radiation. During the daytime, sunlight comes streaming in from above. Some of that sunlight hits the ice crystals and bounces back out to space. Reflected. Gone. This is a cooling effect. The cloud acts like a parasol, shading the ground below. Less solar energy reaches the surface, so the surface is a little cooler than it would have been. But there is a second effect, and this one works day and night. The Earth's surface is warm. It radiates heat upward in the form of infrared radiation, what we call long-wave radiation. This infrared energy is trying to escape to space. But those ice crystals up in the cirrus cloud intercept some of it. They absorb the infrared and re-emit it, some of it going upward and continuing to space, but some of it going back down toward the surface. The cloud acts like a blanket. It traps heat. This is a warming effect. So you have two competing things happening. Cooling from reflecting sunlight, warming from trapping heat. And the net result, the thing that actually matters, depends on which effect wins. For thin, high ice clouds like cirrus, and like the contrail cirrus that airplanes create, the warming effect tends to win, not by a huge margin, but it wins. On average, over the whole globe, persistent contrails and the cirrus clouds they turn into produce a net warming. They trap more heat than they reflect. Let me make this more concrete. Imagine you are standing in a field on a clear winter night. The sky is black, the stars are out, and it is cold. You can feel the heat leaving the ground. The Earth is radiating energy into space, and nothing is stopping it. Now imagine a thin veil of cirrus clouds slides in overhead. You might not even notice it, it is so thin. But the temperature on the ground stops dropping as fast. Maybe it even ticks up a fraction of a degree. That cloud is intercepting some of the outgoing heat and sending part of it back down. You are standing under a very thin, very high, mostly transparent blanket. That is what contrail cirrus does, multiplied across entire continents and oceans. And the arithmetic is not symmetric. During the day, the cooling from reflected sunlight partially compensates the warming from trapped heat. But the compensation is not complete, because ice crystals at high altitude are not very good reflectors compared to the thick, puffy cumulus clouds you see at lower altitudes. High, thin ice clouds let most of the sunlight through. They are semi-transparent in the visible range. But they are quite effective at absorbing and re-emitting infrared radiation. So the warming wins, even during the day, though by a slimmer margin. At night, there is no contest at all. One study looking at roughly 40,000 cases of contrails embedded in cirrus found that about 82.5% of them had a net warming effect. The warming cases overwhelmed the cooling cases. And the nighttime contrails, which accounted for about 38% of observations, contributed a disproportionately large share of the total warming. This day-night asymmetry is one of the most important features of contrail climate science, and it has practical consequences we will get to shortly. Now here is the part that surprises most people. And it surprised the scientists too when they first put the numbers together carefully. The warming caused by contrails and contrail cirrus, right now, today, is roughly comparable to the warming caused by all the carbon dioxide that aviation has ever put into the atmosphere. Think about that for a moment. All the carbon dioxide from every airplane that has ever flown, accumulated over more than a century of powered flight, produces a certain amount of warming. And the contrails, these temporary fleeting ice clouds that last a few hours at most, produce a warming effect that is in the same ballpark. Some estimates say contrails are even a bit larger. How can that be? How can something that lasts a few hours compete with something that lasts centuries? The answer is volume. At any given moment, there are thousands and thousands of commercial flights in the air. Each one that flies through cold, humid air at cruising altitude is potentially making a contrail, and many of those contrails persist and spread. So even though each individual contrail is temporary, the system as a whole is continuously generating new ones, like a river. No individual water molecule stays in the river for long, but the river is always there. And here is another piece of the puzzle that makes this even more interesting. The warming and cooling effects of contrails are not evenly distributed across the day. During the daytime, you get both effects, the sunlight reflection and the heat trapping. They partly cancel each other out, but at night there is no sunlight to reflect. The cooling effect disappears entirely, only the warming effect remains. A contrail drifting through the sky at 2 in the morning is purely a warming agent. It is trapping heat, with nothing to compensate. This means that red-eye flights, the ones that cross the sky between sunset and sunrise, are disproportionately responsible for contrail warming. A relatively small fraction of total air traffic flies at night, but that nighttime traffic contributes a much larger share of the contrail warming effect. If you could somehow eliminate all nighttime contrails, you would knock out a big chunk of the problem. And the geography matters too. Contrail warming is not spread evenly around the globe. It is concentrated along the busy flight corridors. The eastern United States, Central and Western Europe, the North Atlantic, where hundreds of flights per day funnel into a handful of narrow tracks between New York and London, between Chicago and Paris. Southeast Asia, where air traffic has been growing explosively, these are the regions where the sky is most affected. If you live under one of those corridors, the contrails overhead are not just a visual curiosity. They are a measurable part of your local energy balance. In contrast, over the southern oceans, over Africa, over much of South America, there is almost no commercial air traffic at high altitude. The skies are essentially contrail-free. This geographic concentration means that contrail warming is a regional phenomenon as much as a global one, even though the heat it adds is eventually distributed around the planet by atmospheric circulation. Let me take you somewhere specific now, because there is a piece of history that brought all of this into sharp focus. It was not planned as an experiment. Nobody would plan such an experiment. But nature, or rather human tragedy, gave us one. On September 11th, 2001, all commercial air traffic in the United States was grounded. For roughly 3 days, from the middle of September 11th through September 14th, the skies over America were empty. No contrails. For the first time since the jet age began, the busiest airspace in the world fell silent. Well, almost silent. On September 12th, a handful of military aircraft flew between Virginia and Pennsylvania. Just 6 planes. And researchers watched what happened. Those 6 aircraft, flying through humid upper atmosphere air, produced contrails that spread and merged and grew until they covered roughly 7,700 square miles. 6 planes, one morning. Enough artificial cloud to blanket an area the size of a small state. That gives you some sense of the amplification that happens when a contrail finds the right atmospheric conditions. The airplane provides the seed. The atmosphere provides the growth. But the bigger picture came from the silence. Climatologists understood immediately that they had a once-in-a-lifetime opportunity. A researcher named David Travis, working at the University of Wisconsin at Whitewater, along with Andrew Carleton at Penn State and a colleague named Ryan Lauritsen, grabbed the data. They looked at surface temperature records from weather stations across the entire continental United States. Specifically, they looked at the diurnal temperature range, which is the difference between the daytime high and the nighttime low on a given day. What they found was striking. During those 3 contrail-free days, the diurnal temperature range increased. It went up by about 1.1 degrees Celsius, roughly 2 degrees Fahrenheit, compared to the 30-year average for those same calendar dates. The days got a little warmer, and the nights got a little cooler. The gap between day and night widened. This is exactly what you would predict if contrails were acting like a thin blanket over the country. With the blanket in place, the days are a bit cooler because the blanket reflects some sunlight, and the nights are a bit warmer because the blanket traps some heat. Remove the blanket, and the days warm up and the nights cool down. The range gets bigger. Now, 3 days is not a long time. You have to be careful with the statistics. The weather during those 3 days could have been unusual for other reasons. There was, in fact, an area of high pressure over parts of the country that could have contributed to clear skies and a wider temperature range. The researchers knew this. They accounted for it as best they could. They checked satellite imagery and found that while natural cloud cover was light on September 11th, it actually increased on the 12th, 13th, and 14th. So the sky was not clear because of dry weather. It was clear because there were no airplanes making contrails. Subsequent studies have supported the basic finding. Researchers compared regions of the United States where contrails form frequently with regions where they do not, matching for similar surface conditions. They found that in areas with heavy contrail activity, the diurnal temperature range was compressed. The days were cooler and the nights were warmer than in comparable areas without contrails. And this effect showed up not just during a 3-day anomaly, but in long-term records. There is even a mirror image version of this story from the opposite direction. In May of 1944, during the Second World War, the Royal Air Force launched a massive bombing raid over England as a staging operation. More than 1,400 heavy aircraft flew in concentrated formation, and the contrails they produced were dense enough to measurably affect the temperature on the ground below. British scientists, looking back at the weather records decades later, found that daytime temperatures in the affected regions dipped, consistent with the contrails reflecting sunlight. Where the September 2001 grounding showed what happens when you remove contrails, the 1944 raid showed what happens when you suddenly add them in enormous concentration. The physics tells the same story both ways. A NASA researcher named Patrick Minnis went further. He analyzed decades of cloud-cover data over the United States and found a steady increase in cirrus coverage, roughly 1% per decade, that correlated with increases in air traffic. His conclusion was provocative. He suggested that the extra cirrus attributable to aviation could account for a substantial portion of the surface warming observed over the United States during a period of nearly 20 years, starting in the mid-1970s. That remains a debated claim, and the uncertainties are real. But it tells you that the scientific community is taking contrail-driven cloudiness seriously as a climate factor, not just a curiosity. Let me pull back even further now and show you something else that makes this story richer and stranger. I told you that a contrail forms when the temperature is below a critical threshold, that Schmidt-Appelmann line we discussed. But there is a second condition, and this second condition determines whether the contrail matters or not. It is the difference between a harmless puff that vanishes in seconds and a cloud that reshapes the sky for hours. The second condition is this: the ambient air must be supersaturated with respect to ice. Let me explain what that means, because it is beautiful and strange. Air can hold a certain amount of water vapor, and how much depends on the temperature. But there is a subtlety that matters enormously here. The maximum vapor pressure depends on what the vapor would condense onto. For liquid water, it is one number. For ice, it is lower. Ice is greedier. It holds its molecules more tightly. So air can be undersaturated with respect to liquid water, meaning no water droplet could form, and simultaneously supersaturated with respect to ice, meaning an ice crystal would grow happily if one were present. These regions of ice supersaturated air exist throughout the upper troposphere, especially in the mid-latitudes where most commercial aviation occurs. They are invisible. You cannot see them. You cannot feel them. There is no cloud there. But the air is loaded. It is pregnant with water vapor, waiting for something to happen, waiting for a trigger, waiting for ice crystals to appear so it can dump its excess moisture onto them. And along comes a jet engine, roaring through at 500 miles per hour, injecting billions of tiny ice crystals and soot particles into that primed, supersaturated air. Suddenly, the sky has a cloud where there was none. This is the deep point, and I want to make sure it lands. The airplane did not just leave a trail of ice crystals behind it. The airplane triggered a cloud that the atmosphere was already prepared to make. The ice supersaturated air was sitting there, ready, wanting to become a cloud, but lacking the right particles to get the process started. The jet engine provided those particles. And once the ice crystals formed, the excess water vapor in the surrounding air rushed in and made them grow. The contrail became a seed for something much larger. It is like striking a match in a room full of gas fumes. The match does not provide the energy for the explosion. It is the tiniest fraction of the total energy release. But without the match, nothing happens. The jet engine is the match, and the ice supersaturated air is the fuel. And here is a wrinkle that the engineers did not see coming. Modern jet engines are more fuel efficient than the engines of the 1960s and 1970s. They extract more useful work from each kilogram of kerosene. That is good for fuel costs and good for carbon dioxide emissions per mile. But it means the exhaust comes out cooler. Cooler exhaust reaches the condensation point more easily when it mixes with the ambient air. The Schmidt-Appelmann threshold temperature shifts upward, so a more efficient engine can form contrails in air that would have been too warm for an older, less efficient engine. The irony is sharp. By making engines better, we made them better at making clouds, and those clouds warm the planet. This connects to a remarkable thing about the ice crystals themselves. Contrail ice crystals are not the same as the ice crystals in natural cirrus. They are different in ways that matter for climate. Natural cirrus clouds form when water vapor deposits onto whatever particles are floating around in the upper troposphere. Mineral dust, for example, carried up from deserts and dry lake beds. These natural ice nuclei are relatively rare, so natural cirrus tends to have fewer ice crystals, and those crystals grow larger. fewer, bigger crystals. Contrail ice crystals form on soot particles, and jet engines produce enormous numbers of soot particles. So contrails start out with many, many more ice crystals per unit of volume than natural cirrus. And because there are so many crystals competing for the available water vapor, each crystal stays smaller. Many smaller crystals. This difference in crystal size and number matters for how the cloud interacts with radiation. Smaller, more numerous crystals are actually better at scattering sunlight. A fresh contrail, just minutes old, can be more reflective than natural cirrus. If that were the whole story, contrails might be net cooling. But as the contrail ages and spreads, the crystals grow, the crystal concentration drops, and the cloud starts resembling natural cirrus more and more. The optical properties converge. And in the end, the warming effect dominates, just as it does for natural cirrus, but with the added quirk that the contrail created a cloud where none would have existed. It did not replace a natural cloud with a slightly different cloud. It added cloud cover to the sky. That is the key. It is extra cloud. Extra high, thin, warming cloud. The total amount of extra cloud cover from aviation is difficult to measure precisely, but estimates suggest that in the busiest air corridors, contrail cirrus can increase high cloud coverage by a noticeable amount. Over heavily trafficked regions like Central Europe and the eastern United States, the effect is particularly strong. Over the open ocean, where flight paths converge into narrow corridors like the North Atlantic tracks between Europe and North America, the contrail cirrus can sometimes be strikingly visible in satellite imagery. Long parallel streaks, spreading and merging, covering thousands of square miles. Now let me push you one more level deeper, because recent research has uncovered something that makes this whole picture more complicated and more important. For a long time, the standard image of a contrail was a white line against a clear blue sky. That is what you see from the ground. That is what shows up in photographs. And so when scientists tried to estimate the climate impact of contrails, they focused on those visible lines in otherwise clear air. But a series of studies, some using direct measurements from instruments on passenger aircraft and some using satellite data, have revealed that this picture is incomplete. Many contrails do not form in clear blue sky at all. They form inside existing cirrus clouds. The airplane flies through a region that already has thin cirrus, sometimes so thin it is invisible from the ground, what scientists call subvisible cirrus, and the contrail forms within that existing cloud layer. These embedded contrails are extremely difficult to detect. From the ground, you see a thin cirrus layer, and you have no way of knowing that part of it was seeded by aircraft exhaust. From satellites, the contrail is mixed in with the natural cloud, and you cannot easily separate the two. This means that the climate impact of contrails may have been systematically underestimated, because a large fraction of them were hiding in plain sight, embedded in natural clouds that masked their presence. Over the northern mid-latitudes, which includes Europe, North America, and the busy North Atlantic flight corridor, studies of 7 years of in-flight humidity measurements found that about half of the conditions favoring persistent contrails occur within subvisible cirrus or clear sky. The other half occur within thicker, visible cirrus. And that second half, the embedded contrails in thicker clouds, have an uncertain climate impact. In thin cirrus, an added contrail amplifies the warming. In thick cirrus, the picture gets muddied. Sometimes the extra ice crystals barely change anything. Sometimes they might even produce a slight cooling by increasing the cloud's ability to reflect sunlight without adding much to its heat-trapping ability. In the Southeast Asian subtropics, conditions are different. There, almost 100% of the persistent contrail-forming conditions occur within existing cirrus. The blue sky contrail is essentially a mid-latitude phenomenon. So the question of how much contrails warm the planet is not as simple as counting white lines in the sky and calculating their radiative effect. You have to know what kind of air they formed in, whether there was already a cloud there, how thick that cloud was, what time of day it was, and how long the contrail persisted and spread. This is why the uncertainty in contrail climate estimates remains large. The warming is real. The physics is solid. But the precise number is hard to pin down. Let me give you the best current picture. The radiative forcing from contrails and contrail cirrus is estimated at roughly 50 milliwatts per square meter of Earth's surface. Now, 50 milliwatts per square meter does not sound like much, but spread it over the entire globe, running continuously because airplanes are always flying somewhere, and it adds up. It is comparable to the radiative forcing from all the carbon dioxide that aviation has emitted since the Wright brothers, which had accumulated to roughly 24 milliwatts per square meter by 2006, and has grown since. But here is the absolutely critical difference, and this is where the story takes its final turn. Carbon dioxide, once you put it into the atmosphere, stays there for centuries. Some of it stays for thousands of years. It accumulates. Every flight adds a little more, and it never goes away, not on any timescale that matters to civilization. The warming from aviation carbon dioxide will be with us long, long after the last airplane has landed. Contrails, on the other hand, are gone in hours. If you grounded every airplane on Earth right now, every single contrail and every contrail cirrus cloud would vanish by tomorrow morning. The atmosphere would clear. The warming effect would stop. This gives contrails a peculiar and fascinating place in the climate problem. They are a large and immediate source of warming, but they are also a fixable one. Unlike carbon dioxide, which requires fundamental changes to the energy system to address, contrail warming can in principle be reduced by changing where and when airplanes fly. If you could route aircraft around the patches of ice supersaturated air where persistent contrails form, you could eliminate a significant fraction of the contrail warming effect. The airplane would burn a bit more fuel, taking a slightly longer route, and emit a bit more carbon dioxide. But the net climate benefit could be large, because the warming you prevent by avoiding the contrail is much bigger than the extra warming from that additional fuel. Several airlines and research groups are actively working on this. They use weather forecasts to predict where ice supersaturated regions are, and they adjust flight altitudes and routes to avoid those regions. The idea is not to avoid all contrails. Remember, many contrails are short-lived and climate neutral. The goal is to avoid the persistent ones, the ones that form in humid air and spread into cirrus sheets that linger for hours. The challenge is forecasting. Ice supersaturated regions are patchy, layered, and transient. They might be only a few hundred meters thick vertically. An airplane climbing just 1,000 feet from one altitude to another might pass from supersaturated air into dry air. The contrail would stop. But knowing exactly where those layers are requires very precise humidity data at cruising altitude, which is hard to get. Radio sondes, the weather balloons we launch twice a day, give us some information, but their coverage is sparse over the oceans, which is exactly where many of the busiest flight corridors are. The most promising data has come from instruments mounted on commercial aircraft themselves. A program called IAGOS has been putting humidity sensors on passenger jets since the mid-1990s, collecting measurements along actual flight routes. This data has been invaluable for understanding where and how often contrail-forming conditions occur. It was IAGOS data that revealed just how often those conditions coincide with existing cirrus clouds. Early experiments suggest that you can eliminate a large fraction of the climate-warming contrails by rerouting only a small percentage of flights. The persistent climate-damaging contrails come from a minority of flights that happen to pass through exactly the wrong patch of atmosphere at the wrong time. Some estimates suggest that as few as 2 to 3% of flights are responsible for the vast majority of the contrail warming effect. Avoid those patches, and you solve most of the problem. It is a remarkably targeted intervention. But there is a trade-off, and in physics there is always a trade-off. A rerouted flight burns more fuel. The airplane takes a longer path or flies at a less efficient altitude. More fuel means more carbon dioxide. So you are trading a short-lived climate effect, the contrail warming, for a long-lived one, the carbon dioxide. The question is, does the swap make sense? The current evidence says yes, for most cases. The warming prevented by avoiding a persistent contrail is, on a per-flight basis, much larger than the extra warming caused by the small amount of additional fuel. But this depends on getting the forecast right. If you reroute a flight to avoid a contrail and it turns out the air was dry anyway, you just burned extra fuel for nothing. The accuracy of the prediction matters enormously. There is also the question of the future. Air traffic has been growing steadily for decades, roughly doubling every 15 to 20 years. If that growth continues, and if no mitigation measures are taken, the climate forcing from contrail cirrus could triple by the middle of this century. That is a substantial increase. It would make contrails an even larger component of aviation's total climate impact. But alternatively, if contrail avoidance strategies become routine, if weather forecasting improves to the point where ice supersaturated regions can be predicted reliably several hours ahead, and if airlines adopt small route adjustments as standard practice, the contrail problem could shrink dramatically, even as air traffic grows. This is one of the few areas in climate science where a relatively simple operational change could have an outsized effect. You are not asking people to stop flying. You are not asking for a new kind of engine. You are just asking airplanes to fly slightly different routes on certain days. There is one more twist to this story, and it involves the fuel itself. The aviation industry has been experimenting with alternative fuels, biofuels, synthetic fuels made from captured carbon dioxide and hydrogen. These fuels can be blended with conventional kerosene or potentially replace it entirely. From a carbon dioxide perspective, they can be nearly carbon neutral if the carbon in the fuel was captured from the atmosphere to begin with. But what about contrails? Here the picture is encouraging. Alternative fuels tend to burn cleaner. They produce fewer soot particles. And soot particles, as we discussed, are the condensation nuclei on which contrail ice crystals form. Fewer soot particles means fewer initial ice crystals. And fewer ice crystals means a thinner contrail with different optical properties. The contrail might still form, because the water vapor is still there and the air is still cold, but the resulting cloud would be optically thinner and shorter lived. Its warming effect would be reduced. Some researchers have gone even further and considered what would happen if aviation eventually switched to hydrogen fuel. Burning hydrogen produces no carbon dioxide at all, only water vapor, and no soot. So contrails from hydrogen-powered aircraft would need to form on whatever background particles happen to be floating around in the upper atmosphere, mostly natural aerosols. This would likely produce contrails with far fewer ice crystals, and those contrails would persist less often and have a smaller climate impact. Interestingly, the Schmidt-Appleman threshold temperature for hydrogen combustion is about 10 degrees higher than for kerosene. Hydrogen engines would produce contrails over a wider range of atmospheric conditions because their exhaust contains so much more water vapor per unit of energy. But those contrails would be thinner and would often fail to persist. So you might see more contrails from hydrogen aircraft, but the contrails that matter, the persistent climate warming ones, would be fewer and weaker. It is a complex trade-off, and the research is still in its early stages, but the direction is clear. Cleaner fuel means cleaner contrails. Let me take a step back now and show you the full picture, because I think it is beautiful in its strangeness. You have a machine, a jet airplane. It is burning fuel to carry people from one place to another. It produces carbon dioxide, which is the long-lived part of the climate problem, the part that requires fundamental technology change to fix. But this same machine is also, accidentally, creating clouds. Artificial cirrus clouds born from soot and water vapor, growing in ice supersaturated air, spreading across the sky, trapping heat, especially at night, and producing a warming effect that rivals the carbon dioxide effect in magnitude. The carbon dioxide warming is permanent and cumulative. The cloud warming is temporary and continuous. They are two completely different kinds of climate forcing, operating on completely different timescales caused by the same process. And here is the part that I find most remarkable. The cloud effect was hiding. For decades, people talked about aviation and climate in terms of carbon dioxide emissions. Burn less fuel, fly more efficient planes, use alternative fuels. All important, all necessary. But the contrail warming was sitting right there, in plain view, those white lines scrawled across every sky, and for a long time nobody appreciated how significant it was. Partly this was because contrails seem so temporary. How could something that lasts a few hours matter for climate? But the answer, as we discussed, is that the system is continuously refreshing itself. Contrails vanish, but new ones form. The river keeps flowing. And partly it was because so many contrails were embedded in existing clouds, invisible, unmeasurable, hidden from the instruments that were trying to quantify them. Only as satellite technology improved, and as instruments were placed on commercial aircraft to measure humidity at cruising altitude, did the full picture start to emerge. Think about what this means for the way we do science. Sometimes the biggest effects are the ones you cannot see. The contrails hiding inside cirrus clouds are a perfect example. The obvious contrails, the dramatic white lines against blue sky, those are actually the minority. Most of the action is happening where you cannot see it, in clouds that were already there, being quietly altered by aircraft that passed through hours ago. Nature is subtle. That is one of the things I have always believed. You look at something simple, a white line in the sky, and you think you understand it. Ice crystals. Fine. Done. But if you keep asking questions, if you keep pushing, you find layers and layers of complexity. The ice crystals interact with sunlight and with heat radiation from the Earth. They spread and grow into clouds. Those clouds warm the planet at night and cool it slightly during the day. And many of those clouds are invisible, embedded in existing cirrus, detected only by careful measurements from space and from instruments riding along on the very airplanes that create them. And then the whole thing connects to a larger question about how humans are changing the atmosphere. We talk about greenhouse gases, and that is right. That is the biggest part of the story. But we are also changing the clouds. Every airplane that flies through a patch of ice supersaturated air is seeding a cloud that would not have existed without it. We are adding clouds to the sky. Not all clouds, not everywhere. But in the busy air corridors of the northern mid-latitudes, in the flight paths between Europe and North America and across Asia, we are making the sky cloudier than it would naturally be. And those extra clouds are having measurable effects on temperature. One of the things that fascinates me about this whole subject is how the most visible phenomenon was actually the smallest part of the story. The dramatic white lines in the sky, the ones you photograph and post on notice boards, those are often the short-lived contrails in dry air. They look impressive but vanish quickly and do very little to the climate. The real climate actors are the subtle ones, the persistent contrails that spread into sheets so thin you barely notice them, and the embedded contrails hiding inside existing cirrus where they cannot be seen at all. Let me bring this back to the simplest possible statement, because after all this complexity, the simple version is still true and still powerful. A jet airplane draws a white line across the sky. That line is made of ice crystals. If the air is dry, the line vanishes. If the air is wet, the line grows into a cloud. That cloud traps heat. The Earth gets a tiny bit warmer. Multiply that by millions of flights per year, and the tiny bit adds up. And the truly remarkable thing is that unlike most of the climate problem, this part could be fixed quickly. By changing the routes of a relatively small number of flights, the cloud was never necessary. It is a side effect, an accident of combustion in cold air. I love this kind of thing in physics. You start with something that every child has noticed, the white line behind an airplane. And by the time you finish pulling on that thread, you are deep into thermodynamics, radiative transfer, cloud microphysics, climate science, and the strange way that human technology can alter the sky itself. The sky is not a passive backdrop. It is not just the blue space above your head where weather happens. It is an active, dynamic system, and we are participants in it now, whether we intended to be or not. Every time an airplane flies through the right patch of cold, moist air, it leaves a mark. A temporary mark, yes, but a mark that changes how energy flows through the atmosphere. A mark that changes the temperature on the ground below. You know, in physics, we sometimes draw a hard line between the things humans do and the things nature does. Over here, the engineered world. Over there, the natural world. But contrails erase that line. A contrail is a natural cloud produced by an artificial event. It obeys all the laws of thermodynamics and radiative transfer that govern every other cloud in the sky. It is made of ice. It interacts with sunlight and infrared radiation. It grows and spreads and eventually dissipates, just like natural cirrus. But it would not exist without a jet engine. The atmosphere did not call for this cloud. We called for it accidentally by burning kerosene 6 miles up. And because it is a real cloud, it has real effects, not pretend effects, not theoretical effects. Measurable, observable, quantifiable effects on the flow of energy through the atmosphere. When we fly airplanes, we are not just transporting people and goods. We are participating in the planet's radiation budget. We are actors in a system that determines how warm the surface gets. That is an extraordinary thought if you let it sink in. The most humbling thing about physics, I have always felt, is the way it connects things that seem unrelated. Who would have thought that the business of flying people from New York to London has anything to do with the temperature of a farmer's field in Ohio at 3 in the morning? But it does, through ice crystals, through radiation, through the atmosphere's delicate energy balance. The connection is real, it is physical, and it was invisible until somebody thought to look for it. Next time you look up and see that white line, I want you to see more than a pretty streak. I want you to see a cloud being born. I want you to think about the cold, the ice crystals, the soot particles. I want you to wonder, is that contrail going to vanish, or is it going to spread? Is the air up there dry or wet? Is it daytime, where the contrail partly cools the surface, or is it drifting overhead at night, when only the warming matters? And then I want you to think about this, that cloud, which was made by accident, which nobody designed, which exists purely as a byproduct of getting people from one city to another, that cloud is actually changing the planet's energy balance in a way that is measurable from space. The simplest things in nature are never really simple. That is what physics teaches you, over and over again. You think you are looking at a white line. You are looking at a piece of the climate system. And if that does not make you stop and stare a little longer, I do not know what will. So tell me, the next time you see a contrail stretch out and spread, staying there for an hour, 2 hours, slowly turning into a hazy sheet of cirrus, what do you think that sky is going to do differently that night?